Hi guys. Okay, now let's talk about simple chemical kinetics. Consider the following simple chemical reaction. Let's say we're going to take A and convert it into B, right? Now this is distinct from the way we've been talking about a process like this, right? For the whole part of this course up to this point, we've been considering something that is essentially in equilibrium. We know we have an associated dissociation constant. But now we're going to break away from the assumption that we're at equilibrium. In fact, specifically, we're going to assume we're not at equilibrium. So in this case, we're now going to say, what happens if we're just thinking about a process that irreversibly converts a substance A into B? So we start with pure A, and it's now going to turn into B. And what we're really interested in now is the temporal progression, right? Right? In other words, how fast does this happen? Okay. All right. So we know the speed of a process. We're going to think about how fast something happens. We know we can think about that in terms of rates, right? Which is what we're going to do. So we can define the rate of this process as equal to, or using the symbol V, right? Is going to equal the reaction rate, right? And we know we can probably define V fairly easily. We can say, well, V has got to simply be equal to the rate of change. I'm going to use differential notation here. The rate of change of the concentration of A with respect to time. It gets a minus sign because it's changing, right? It's decreasing, right? And that is going to be exactly equal to the rate at which B is formed, right? So in a positive sign with respect to time, right? Note the units of this process. The units of B, right, are of course, this is going to be in sort of concentration per time, unit time, which in our case, it's almost always going to be in, say, molar per second or per minute or micromolar per second, right? So we're going to be, since we're in solution, we're talking about sort of molar concentrations per unit time. Okay. All right. So there's our basic expression. The problem is that alone, okay, we sort of define what we want to be looking for, but we've got to relate that to something, right? How is this process taking place? Well, let's think about that, right? Think of a slightly different way. Let's say, well, I know what I'm interested in is sort of a change in the concentration of A. So I can write this out a different way, sort of step away from differential notation for a minute and say, well, let's think about this as a change in the concentration of A. Right? What's that have to be equal to? Well, I don't know what it's going to be equal to first, but I can start by thinking about proportionalities. What turns out it has to be proportional to is the concentration of A I start with times time, right? Or change in time, right? Because we're delta time. So the change in the concentration A is going to be proportional to the amount of A I've got to start with times the amount of time that I consider that change in concentration of A over. Okay, well, we know, because we've talked about this a few times, I can convert any proportionality into an equality with a constant of proportionality. So I could rewrite this as delta concentration of A is going to be equal to, and we're going to use a particular symbol here. It's going to be a lowercase Arabic K, concentration of A with respect to time. Okay, cool. Turns out that that expression, that basic relationship where the rate of change of, or the magnitude of the change of a substance or something is equal to, or is directly proportional to, the amount you start with, the amount you've got at any given time, times the delta t, change of time, is an incredibly common process in our universe, right? Occurs again and again and again in terms of the temporal behavior of how things change. And a really common analogy here is to think about this with respect to radioactive decay, all right, which has the same basic relationship. But personally, I don't find that one to be terribly intuitive. So I'm going to give you another one, right? If the intuition for why the rate of change or the amount you've got is going to be proportional, the amount that something changes is going to be proportional to the amount you start with, is not sort of just intuitive for you, and it isn't to a lot of people. Think about it this way. Imagine I have a tank full of water, right? With a pipe out of the bottom of it. Right, and my tank, like I said, is going to be full of water. All right, and so water can come running out of the tank. So the question is, what's the flow rate proportional to? Or asked another way, as water flows out of the tank, right, the volume in the tank is going to change, right? There's going to be some change in volume. What's that proportional to? All right, now I know it's proportional to the size of the tube and temperature and everything else, but leaving all that aside, right? Taking it as an assumption that it's a reasonable sized pipe or, whatever. In this basic situation, what's that change in volume proportional to? It's proportional to the volume you start with times time. That makes some sense, right? More water that's in the tank, the faster the volume is going to change. And as the volume decreases, the flow rate's going to slow down because there's less mass in the tank and the hydrostatic pressure is going to decrease, right? So that's one you can kind of get your brain around, because since we were little kids, we sort of played with that sort of idea. It's the same basic configuration we've got here with respect to this process of that chemical conversion of A into B, right? Same basic fundamental idea. All right. So this proportionality constant, K, that's a really important parameter, right? It's more than just a proportionality constant, right? It's known as a rate constant. Right? And it's directly related to the probability per unit time that A is going to turn into B, right? So it sort of defines in many ways the temporal behavior of this process within the simple mathematics that describe it. It's the governing sort of the parameter constant, right? So another way to write this out then, or let me just go back and write out what we had before again, which was now we have A goes to B, to where we started again. And we know we've got this fundamental rate constant that's associated with this process. Again, it's a lowercase k, right? Keep in mind, uppercase k's, those are equilibrium constants. Lots of people get this confused. The lowercase k, that's a rate constant, all right? Don't forget that one. They mean fundamentally different things, okay? All right. So that's our basic expression. We now, hopefully, you guys have some intuitive feel for why the process is going to behave the way it does. So let's see if we can solve this. So let's go back to that change delta expression I had before. So we know that delta A has to just be equal to K times concentration of A. Oops, I dropped my concentration bracket. Sorry about that. It's an old habit. Times time, or times delta T, right? Okay. Well, we can rearrange that, right? So maybe let's sort of rearrange that, right? Delta concentration of A divided by delta T just equals K concentration of A. Huh. Well, that's something that doesn't look completely insane, because if we switch back to differential notation, we have D concentration of A with respect to time is just equal to K times the concentration of A. Huh, that ought to look familiar because remember up here, we know that that's sort of the expression we're looking for that describes the rate. That's cool because now we just came up with a so-called, what this is sometimes known as a rate equation that describes that process, right? That's cool. That's cool. Notice one thing. What are the units of that rate constant have to be? Remember, the way we defined this before, and it's just sort of implicit in the way that differential is written down, the rate, right, is going to be, let me write this out a slightly different way here for you guys. So remember, this is equal to that rate of change, V. And remember, what were the units of V? Molar per unit time. I'd say molar per second, for example. All right, well, if A, concentration of A is in molar, what does that mean the units of K have to be? Molar per second. They have to basically be inverse time. Time minus 1, say second minus 1, minutes minus 1, whatever, right? Okay, so this rate constant is going to have units of inverse time, right? Okay, notice something else. What we've basically written down here, if you remember some of your basic mathematics, is we've written down a very simple, one of the simplest possible ordinary differential equations, right? We've got a simple derivative over here on the left that equals this constant times A, right? Because the variable here is has a power of unity, right? This is a so-called first order differential equation. And this is the rate constant here is going to be known as a first order rate constant. Sometimes this is also known as a unimolecular rate constant. And that makes some sense because our basic process here is just the conversion of one thing into another, right? There's no binding on it. It's just basically a unimolecular process. And you guys hopefully kind of remember that. All right. So the trick is we need to solve that equation, right? Anybody who remembers their basic differential equations, this is always the game. You define your basic differential equation, and then you got to solve it because what you're really after is a function that will predict the behavior of your dependent variable with respect to some other independent variable or variables, right? And that's what you want to know, and that's what we want to know here is because we want to be able to predict as a function of time how much A we have left or how much B we're making per unit time. So to do that, we've got to solve this basic expression. All right, so how do we do that? All right, I'm going to go down here. I'm going to write that out again, make it a little clearer over here. So we're just going to write out our little differential equation again, where I have a little more space. So this again was our expression. Differential change in the concentration of A with respect to time is just equal to K times the concentration of A. All right, how do we solve that? Turns out there are two basic ways, right? There's the so-called right way, or I would say like the mathematician's way, right? Where if you remember your basic differential equations, you got to separate your variables, right? And this one's trivial, right? So you separate your variables. We're going to run an integral from between our two conditions, A0 to A. You write this out. The separation would look something like this: 1 over concentration of A dA is simply equal to the, oops, let me space that out a little bit more. Pull the minus sign in the K, outside of the bracket. Now you'll notice in this case, I pulled the minus sign over. That's just sort of a common way to do this. Could leave it on the other side, but you know, most of the times you'd solve this, you pull the minus sign to the right side. So that's a constant, K is a constant, and now we need to integrate because we pulled our other variable over here with respect to time. All right. Okay, cool, right? So you can run through that integral, right? And you'll find out, of course, that that's going to end up being a natural log. Integral that 1 over that variable is going to be a natural log. You run through the definite integral, of course. You then apply some laws of integrals. You get log of a0 over a is going to be equal to minus kt, which you can then go on and solve. All right, so you can go through all of this, right? There's nothing wrong with it, right? There's another way. You can bypass all of this, where you can just guess, which is sometimes as productive a way as the rigorous way. And in that case, the guess would be what function, when derivatized, right? What function, when derivatized, returns itself. So here's our function, a, when derivatized, returns itself times a constant. Well, maybe remember, in either case, you do it the rigorous way, or you do it by remembering that little piece of mathematical trivia. Turns out the solution is simply that the concentration of A with respect to time is simply equal to the concentration of A I start with times e to the minus kt. It's a simple exponential decay, so-called exponential decay. And that is your first so-called rate law. So the integration solution of a rate equation yields a rate law, and that's the simple exponential rate law, right? So like I said, this is a really common process in our universe where the rate of change of a process that only depends on a unimolecular event is described by a simple exponential, right? And there's our rate constant right there as this multiplier to our independent variable in the exponential function, right? Okay, that's great. Now, we know physically that's what's going to have to go on. Question now is, from a practical point of view, you're doing work in the lab, how do you find that variable? In principle, I mean, you know, maybe you've met, you know the amount of A you started with, and this you're measuring, say, because you can do an experiment. Like we talked about before with respect to binding, we want to describe a process like this experimentally. The thing we want to know usually is that key constant that describes the process, which means we got to go figure out a way to get K, right? We got to find a way to extract K from some experimental data. We'll talk about that next.